So let's look at an example that is simulating that experiment we saw uh, in the last presentation. And so here we have a doubly charged helium atom whose mass is 6.6 times 10 to the minus 27th kilograms is accelerated by a voltage of 2700 volts. What will its radius of curvature if it moves in a plane perpendicular to a uniform 0.34 Tesla field? Tesla is the unit of magnetic field. And what is its period of revolution? So we are given the mass of the atom is 6.6 times 10 to the minus 27th kilograms. We are given the charge Q of the atom is equal to twice the charge, and that's we have that as electron charge, and that's 2 times 1.2 times 1.69 times 10 to the minus 19th coulombs. We have the potential of the atom is equal to 2700 volts, and the magnetic field is 0.340 Tesla. So for part A, we'll look at this in terms of energy. So it's energy initial. See if I can write this a little better. Energy initial is going to be equal to energy final. So the initial energy is the energy that is given the atom. So that's going to be Q atom times the potential and that's just going to equal our final, which is this atom in motion, and that's just equal to 1/2 mass of the atom times the velocity of the atom squared. And now I can solve for the velocity of the atom, and that's equal to the square root of 2 Q atom times voltage atom, or potential, over the mass. Now, the force is going to be maximum because it says it's perpendicular to the field. So that's just going to be equal to Q of the atom times the velocity of the atom times the magnetic field. And that's just going to equal the force, and this will be the centripetal centripetal force, which is going to be mass of the atom times the velocity of the atom squared divided by r. So we can calculate r. R is going to equal the mass of the atom times the velocity of the atom divided by the charge of the atom times the magnetic field. And if I insert the potential in and do some simplifying, I get that R equals 1 over the magnetic field times the square root of 2 times the mass of the atom times the potential divided by the charge. And if I insert my values, and we evaluate that, our radius is going to equal approximately 0.031 meters, or that's equal to about 3.1 centimeters. Now we can look at part B, and there we need the period of the revolution. Well, we know that the velocity has to equal the distance of the path. Well, that's just going to be 2 pi times the radius, because that's the circumference, divided by the period. And the period is what we're looking for. So the period is equal to 2 pi r over the velocity of the atom. So let's figure out the velocity of the atom first. We have V atom is equal to square root 2 times the charge times the potential over the mass of the atom and make sure we take square root of everything, and we get a velocity of 5.117 times 10 to the 5th meters per second. And if we put that back into our formula, 2 pi times 0.031 meters over 5.117 times 10 to the 5th meters per second, our answer comes up to about 3.811 times 10 to the minus 7th seconds, and that would be equal, well, if I'm going to go to the next multiplier down, it would be milli, micro, nano. That would be -9. So I need to move my decimal places twice. So that's 381.1 nanoseconds. So that gives us an idea when we look at that experiment just how small that radius is and just how fast those particles are moving to make that circle.